Well, good evening. I've got a couple of guests, and I'm not going to reveal who they are until the very end today. Maybe you can figure it out, maybe you can't. There's one from each class, one from 6th grade and one from 7th grade pre-algebra. And the three of us together are going to be talking about Lesson 3.8, which is on problem solving. Okay, now, problem solving is something that we do every chapter. We do problem solving of some sort, and what we're going to be talking about today, don't worry about it, what we're going to be talking about today is a problem solving method called simplify the problem. And as you can clearly see, I clearly am emphasizing what words here, guys?
Simplify!
Right, simplify. So you're going to take the problem and you're going to try to find a way to simplify down to what's really happening. Okay, and then figure out the answer. Now, sometimes we can oversimplify. So I've got a really cool problem worked up here for you. And so this is a problem that I like to call the snail problem. So what I want you to do is I want you to imagine that we have a well, like a well you get water out of. And let's say that a snail falls in the well, and the snail wants to climb its way out. Now, the snails are not usually known for speed, and so this particular snail, this is a really slimy well on the inside, so the snail can climb up, and he can only get about 2 foot per day. But then he's got to rest. He's got to take a break, and when he's resting, because the wall is so slippery, he actually slides back down a foot. So every day, he climbs up 2 feet, then he goes to sleep, and he slides down 1 foot. And that happens each day, up 2, down 1. Now, suppose that the depth of the well from the beginning is 20 feet deep. All right. So what we've got to do is we've got to figure out how long it's going to take the snail to get out. All right. So once again, picture the snail. And so here we go. We'll draw what the snail's doing. So he goes up. So this is in 1 day.
Blue.
Okay. In 1 day, the snail goes up 2 feet, but then he slides back down
1 foot.
1 foot. All right, and what we're after here is if you kind of put that together, it doesn't take a rocket scientist or even a pre-algebra student to figure out that what is the snail actually accomplishing in a day?
1 foot.
Yeah, he's accomplishing 1 foot. Does that make sense?
Mm-hmm.
Okay, so he goes up 2, down 1. I guess I should put a 1 in there. Down 1 foot. Okay, so the net result, which is kind of the simplified part, the net result is that the snail goes plus 1 foot per day. So if it's 20 feet down in the well, how long will it take the snail to get out?
20 days.
You're so smart.
Oh my gosh!
You're also wrong. Now that's the basic idea. So we did simplify the problem down, and we do figure out that the snail gets 1 foot a day. However, actually, the snail gets up 2 feet and then slides down 1. So if the snail climbs up for 18 days, at 18 days, how far will the snail be? Well, the snail will have actually got as high as 19 feet, but then in reality, he only gains 1 foot the last day because he slid back down. But if he's at 18 feet at the beginning of the 18th day, how long does it take to climb the last little ways out? Well, he only needs to go 2 feet, and once he gets to the edge, will he slide back down anymore?
No.
No. So actually, the answer to this one is 19 days. So that's why I said we're going to simplify. So this is the idea over here of simplifying. The net result was 1 foot per day. However, we don't want to oversimplify because sometimes the very end might have a little bit of a trick in store for us. So that's a great example. So this is the idea of simplifying the problem, this idea of coming up with the net result of how much the snail achieves in a day. But we also have to be careful about the end. So let me give you another example. That's all we're really going to do, because what we're going to do tomorrow is I'm going to give you some practice problems, and you can just go about trying to figure some of them out. And I'll give you a choice like I usually do with problem solving. All right, let's go to the next example. Okay? So what I've drawn, and this isn't a perfect drawing, but let's say I draw a perfect 4x4 square made out of little squares. And I want to know how many squares there are total of all the different sizes. Okay? So what I'm going to do in this case is I'm going to simplify it down to examining the cases. All right? So let's start with the big giant square. How many 4x4 squares are there?
Well, 4.
that are 4 wide and 4
Oh,
wide?
no, sorry, 1.
There's only one, right? Just the big one.
Yeah.
All right. But what about if I do a little bit smaller square? What if I do a 3 by 3 square? Well, there's one in this corner. There'd also be one in this corner. There'll be one in this corner. And there'll be one in this corner. So the 3 by 3 squares, there's how many of them? Well, 1, 2, 3, and 4. So there's 4 of those, right?
It makes sense
All right.
now.
What about the 2 by 2 squares? All right, that's these guys right here. Well, there's 1, 2, 3 going across the bottom. But then I'd also could go across these 2 rows, right? And then that'd be 3 more. That'd be 6. And then I could also go across the top 2 rows. So there's a total of 9 of those. All right. And then finally, how many individual squares are there?
16.
4 by 4 is, yep, I agree with both of these guys. The 4 by 4s, there are 16 of those.
Correct, Watson.
I'm sorry, the 1 by 1s, I should say. The 1 by 1s are 16. So if I add this all up, how many total squares did I accumulate? Well, actually, an easy way to add this, what's 1 plus 9?
10.
Yep. And 4 plus 16 is?
20.
20. All I did is a little commutative property. Really what I did is I switched the order of the 4 and the 9. And so 10 and 20 is 30 total squares.
Yay.
Okay. So in both of these cases, by kind of simplifying, don't try to think about the whole thing all at once. Do it all in our heads and just solve for the answer. Instead, let's go ahead and break it up into kind of a simpler problem and then figure out one simple problem at a time. So in the snail problem, we figured out that, look, basically the snail goes up 1 foot a day. All right? So it's almost a simple division problem except for that one last day where he doesn't slide down. So it was basically 20 days, but he actually got out 1 day early on good behavior because he didn't slide down. Okay, on this problem with the squares, what we did is we just broke it down by looking at how many different arrangements. All right, so the only question I'm going to pause, or I'm going to have you, that I'm going to pose to you all, is who do you think my 2 volunteers are? So from 6th grade, think about who you think the volunteer is. And then from 7th grade, think about who the volunteer is. He didn't say very much, but
First name, last name.
there we go. But you've seen him in quite a few videos before. So, so get those names in your head and see if it matches the last slide. There we go. There's my buddies. And you may or may not recognize these guys. You 6th graders, you'll recognize this funny-looking guy. And 7th graders, you'll recognize this fella. For those of you in 6th grade, you probably may not know him, but this is Ben. He's been in a bunch of your videos. And 7th graders, you may not know all the 6th graders, but this is Austin. Okay, so Austin and Ben, thank you very much. And that's it for the video tonight. We'll see you guys tomorrow in class when we'll do some problem solving. So come ready to really read the problems carefully and think.
Fuzzy hair.
We'll see you tomorrow.